Okay, so today we're going to finish our discussion of how to construct the coarse-grained free energy of a system, the Ising model in particular, and I'm going to show you how we do it phenomenologically using symmetry and analyticity, which is what we started doing last time, and then I'm going to show you some aspects of the microscopic derivation, as it were, from the original Hamiltonian. So there's a bottom-up description where you start from the microscopic and you calculate, and there's a top-down where you just use symmetry and analyticity and construct things for yourself, and hopefully you get the same answer when you do both of those things. And then along the way, we'll discuss which one is the more convincing. Then the second thing we'll be doing, the third thing that we'll do in today's lecture is we'll make a start on the normalization group. So finally, we are going to get there. And we will start off by motivating the Kadanoff scaling picture, and which was the foundation for the normalization group. All right, so last time we were very conscious about the different levels of description that we use. So here at the top level, over here, we start off with our microscopic description of a lattice with spins defined on a lattice, either up or down. And then we constructed a coarse-grained description where we said, let us take a local average of the spins within a distance of this continuum point R, plus or minus this window size lambda over 2. And then we move this along, average the spins within that distance, and then construct this coarse-grained continuous function in a continuous space. It's continuous in two ways. One, the variable is a continuous variable between -1 and 1, and also it's a function of a continuous spatial variable rather than a discrete variable. And all of those simplifications mean that we can use calculus and things like that, tools that we know and love. And so I've drawn you a picture there of what a coarse-grained magnetization profile would look like for the microscopic spin configuration that I sketched. And then what we want to ask is, if I know such a coarse-grained order parameter, a coarse-grained magnetization, then what is the probability of observing that when I'm in thermal equilibrium? And the answer is, like a Boltzmann factor, e to the minus beta times some free energy divided by a partition function, normalized, and that free energy is called the effective free energy. That's L lambda. L stands for Landau. Landau first wrote down this idea of a Landau free energy. The scale of coarse graining lambda is going to determine what M is and therefore what L is. So I've indicated that explicitly as a label, but frequently we'll forget to do that. And so then the question is, if that's going to be what is the probability distribution? How do we construct it? And so what we started doing last time was we said, well, if I take mean field theory, or I take a series of spins and I work out the magnetization per spin, and then now I want to work out what is the free energy that corresponds to that in a uniform system. So what I do is I take the equation of state that we derived from mean field theory a couple of lectures ago, and then I ask, that equation of state came from differentiating a free energy with respect to M and setting that equal to 0. So if you look at what's here in the square brackets, that free energy, if I then differentiate it with respect to M and set it equal to 0, will give me the equation of state that we had derived from doing our mean field theory. And so I put in a factor of 1/12 there, which will then give us the 1/3 that we explicitly derived. So if that's what it could be, the coefficient might in general be something different, but that's consistent with our mean field theory. So that's the mean field theory. Take the free energy per spin, multiply it by the number of sites or the volume of the system, and that's how you get the Landau free energy. But that doesn't have any spatial information in it. So the next thing you say is, well, just take that, but now just take that function and apply it locally in space. So all I do is I take this formula up here, and then I just make M now a function of space, as I've shown you in the second line, as I've shown you down here. And now the question is that the way that we generalize the mean field theory? And so you might say, well, it's got to be something to do with it. M is now a function of R, so it's spatially varying. So instead of just summing over every lattice site and multiplying by how many lattice sites, now we have to integrate over space, and we have to integrate over space and divide by a to the d, which is the lattice spacing. So you get something like the equation at the bottom. And then you say, well, are we done yet? And the answer is no, we're not done, because we've neglected the cost of making a spatial gradient in the free energy. So in other words, if I have a uniform system, and now I say I'm going to make a deformation of the system, so now the free energy, the magnetization is now varying in space, there should be a cost associated with the spatial gradient. Why? Because if the system is in equilibrium, then it will be in a uniform state, because the equilibrium state will be when everything is spatially uniform. That means that if I make a spatial fluctuation, then there's going to be a cost associated with that. And so we have to compute what that cost is. And that cost isn't going to depend on whether the fluctuation is going down or is going up. There's just a cost to having a gradient in the system. So what we're going to do now is compute what that cost is. And we need that to include that term, because if we don't have this, then in principle, the magnetization could then fluctuate in space arbitrarily fast. And we don't want it to do that. We want it to be this nice smooth profile that I've sketched here on the left. And for that to happen, we have to exclude rapidly varying Fourier coefficients. And so we're going to have to add another term. So now let's construct the next term that we're going to add. So the next term that we have to add, we're going to construct it in the following way. There's multiple ways to say this, but let's think about, first of all, symmetry. So symmetry, we know that L is a scalar. It's a free energy. It's a number. It's a scalar. If I look at m lambda of R, that is also a scalar. If I want to look at spatial variations, of m lambda of R, then the simplest spatial variation would be grad, would be grad of m lambda of R. And that quantity is a vector. So if I want to if I want to say that L is some thing that depends on the spatial gradients of m lambda, the only way I can do that is if I've got a scalar on the left-hand side and the thing inside the scalar, the thing inside the argument here is a vector, then I have to construct this function must be a function that is in fact a scalar function. So the only way that I can construct a scalar function from a vector is the obvious one, which is take its norm. So I could say, for example, I'm going to take grad m dotted with grad m, and then that would be a scalar. So that would be a good thing to do. So then that says then that if we do that, then our formula for the free energy then becomes the following. L is some constant, some arbitrary thing, and now I've got the integral ddr over lattice spacing to d, and then I've got 1/2 t m lambda of r plus 1 in this example, it turns out to be 1/12, then minus h of r m of lambda of r, and then the new term is going to be something that is proportional to grad m squared, and that would be fine. And you could say, well, there could be other terms I could make. I could take grad m squared and square that, and so on. But we're going to just stop at grad m squared, and the reason is that this term here is the lowest order spatial derivative. that will penalize gradients. And we'll see that it is in fact isotropic, so it's spatially uniform, spatially isotropic, and so in other words, rotationally covariant. And why is rotationally covariant? Well, because it's the norm of this vector, so the norm is rotationally covariant. The norm doesn't depend on which direction I look in, and then you might have higher order terms. E.g., you might have grad m squared, that's a scalar, and then square that. So you could do that. But if you think about that in k-space, this is something like order k to the fourth, where k is wave vector. This thing here is order k squared. And so in other words, the term that we've chosen is the lowest order term. Lowest order term for a long wavelength description. And that's what we're trying to do. So that says that the expression that I've written down there is perfectly fine. That's as far as we need to do. And this gamma is a constant. It's not a critical exponent. It's just a number which will tell us some constant proportionality that will tell us how strong is the penalty for spatial gradients. All right. So that is our construction of the Landau free energy, and so what I want to do now is what is slightly generalize all this. So I wrote down specific coefficients here in my Landau free energy, half and the 12th and things like this, just because of the way, just to make it, to show you how it came from our mean field theory. But in general, we could motivate this in a different way. We could say, well, we know that the L should be some L naught plus an expansion in powers of m. So you could say it should be something like that. And then let's now talk about this expansion. Well, this expansion, it must be an even function because of the symmetry in the Hamiltonian. When there's no external field. So then it has to be an expansion in powers of m. So it's going to start off with m squared and then go to m to the fourth. So then I can write that expansion as some a m squared plus b m to the fourth. And usually, I think in my book, I wrote this down in this way. I chose those coefficients to be a and b divided by a half and b over 4, just like that. You can choose them to be anything you like. And then what should be the functional form of a and b? So then the functional form of a and b, well, you know from doing homework 1 that what we expect is that for t less than 0, i.e. t less than tc, we want that the solution of dl by dm is equal to 0 when h is equal to 0. That should give you a solution m is equal to 0, but also a solution where m is not equal to 0. So we know then that if I differentiate dl by dm, that gives me a m plus b m cubed, and that should equal 0. So if a is greater than 0, then the only solution is m is equal to 0. So therefore we need a must change sign as t goes below tc. And so therefore we can write a is equal to some a1, some other number, which is greater than 0, times little t, where a1 is positive, and then that will ensure that the solution exists, and that has to require then that the coefficient b must be greater than 0. So phenomenologically, we could write down exactly what we found from our explicit construction. We could do it just by using this very simple phenomenological argument. Okay, so these arguments, which use analyticity and symmetry, we call that phenomenological. Okay. And you can think of that. I'll take your question in a second, Andrew. So that we can. So we think of this as a sort of top-down way of making a theory, because just like our 10-second theory that we did in the first lecture in class, this is a theory where you, without knowing anything about the microscopics, without even doing any calculation, you can already construct this free energy. Now, there's other thing I didn't tell you, and which is you might say, let me go back to the left-hand side. You might say, why didn't we add here a term of order m to the 6? And the answer is because we don't need to, because what we're interested in is we're interested in T going to TC. We're trying to make a theory of the critical point. And so that means that M is tending to 0. So M is going to be small. And so therefore we can do a power series expansion and truncate at the lowest order. We can't truncate at M squared, because as I just showed you, the coefficient of M squared has to change sign as I go through to the phase transition. The free energy always has to be bounded below. So the lowest order that we can go is we have to include an m squared term. We have to have an m to the 4th term that is positive so that the Landau free energy is bounded below. So we can say that we need this b m to the 4th term to ensure that L is always greater than 0, well, let me just say not greater than 0, that's misleading. That L is bounded below for all temperatures. If I didn't have the m to the 4th term, I made the coefficient of m squared, the thing called A, if I made that negative, then the system could minimize its free energy by making m go to infinity. And then the free energy would be minus infinity. Well, that's no use to anyone. Okay, we know that's not happening. So we have to have this m to 4th term, and that's why that's the lowest order that we can do in the expansion. So we've done quite a few things here. We've done analyticity, we've done symmetry, we've done positivity, well, bounded below, I should say, bounded below free energy. So we've used all these general arguments to construct our theory. Okay, so Andrew, you had a quick question? Or did I already answer
Well,
it?
it's just about the coefficient of beta. Did you mention why? I believe because I believe in the homework setup you said that we're assuming that it's a constant.
Yes.
Did you just argue a few minutes ago why it has to be a constant?
The coefficient of B, if you think that B is So the coefficient A has to change sign. So it has to go as the first term is proportional to little t. If B, if I made an expansion of B in powers of little t, it would be B naught plus B1t plus B2t squared and so on. Okay, but all those higher order terms, other than B naught, wouldn't matter, wouldn't change the results asymptotically as I go towards TC. So we just can keep the constant B being a constant. Okay. All right, so thanks for the question.
There's a variation, but it's just so small.
It's higher order in things that we need to calculate. All right, so the next thing I want to do is I want to now construct a bottom-up theory. I.e. starting with microscopics. And the way that we technically do that most accurately and most in the most sophisticated way is what you are doing in homework 2. So in homework 2, what you're doing is for a particular infinite range model, you are doing what I'm calling what is known as a Hubbard-Swiatovich transformation, where you take the Hamiltonian, you then decouple the interaction terms, the terms that make it impossible to factorize it, and then you do an expansion in those things, and in the end you'll derive the free energy that way. So that's the sort of professional way to do it, and it's exact if the model has infinite range. So you'll get to do this exactly in homework and see how to construct that. We're not going to do it in that way here. So here what I'm going to do is I'm going to just show you how to construct the gradient term. And the other terms I think are fairly straightforward. So that's our goal, is to construct the gradient term. So let's do that. So we're going to set little a capital H is 0. So our Hamiltonian is now minus j sum over I and j, nearest neighbors, Si Sj, and in general I can write that as some minus sum over I and j unrestricted, some j I j matrix times Si Sj. And what we are expecting is that Jij would be just a constant if the Ri minus Rj, that distance, is less than, say, the range of interactions and is 0 otherwise. And if that range of interactions is the nearest neighbor spacing, then that's what R is. So R could be, for example, R could be the nearest neighbor spacing. But in general, it could be something more than that. So that's what we have. Then what I'm going to do is we're going to define the local magnetization. So I'm going to define that as Mi is equal to the expectation value of Si, and it is not coarse-grained, but later we will anticipate that this will eventually map into the coarse-grained magnetization. So I'm calling it coarse graining and taking the continuum limit. Continuum limit means that my discrete lattice spacing now gets turned into a continuum, a spatial variation, and then I can slide things slowly along from that and then use calculus. So that's called taking the continuum limit. And so what we want to do is we want to then, so what the calculational goal is we want to express the Hamiltonian as a function of these local magnetization. And then we're going to say that that thing is somehow the same thing as the Landau free energy. We're going to see if we can do that. And what I'm going to focus on here is just the gradient terms, because the other ones are fairly simple. So now we're going to just look at the gradients. So what is the way I do that? Well, if I look at my Hamiltonian, so what my Hamiltonian has in it is a term that looks like this, minus sum over I and j, jij, mi, mj. And I'm going to write this in the following way. I'm going to write this as minus, and then I'm going to write it like this. Let me show you the idea. So the idea is, first of all, make a sum over the lattice sites I, and then I'm going to look in the neighborhood of any spin I and look at its neighbors that are within the range R. So I'm going to write this in the following way. I'm going to write this as the sum over some vector whose magnitude is less than or equal to R. And then I'm going to write this as the sum of mi plus delta minus mi over a, this thing squared, minus mi plus delta plus mi over a squared. And you can see, so this thing is, the first term is a spatial gradient. The second term is not. So this is a sort of, this thing is roughly like a spatial gradient, a discretization of the gradient operator. This thing over here is roughly speaking 2m squared, because mi plus delta plus mi, if delta is very close to I, then it's just twice mi. And then to normalize this, I have to write this down as j and then a squared over 4. So the a squared is there because of dimensional analysis. The j is there because that was there in the original Hamiltonian, and then the factor of 4 is there so that this thing is in the continuum limit exactly the original Hamiltonian. So all I've done here is literally rewrite this in a clever way. And just to remind you, my A is my lattice spacing, like that. All right. And so delta is basically some vector that points in the different directions, in this direction, this direction, this direction, this direction to the neighbors. And if it's next nearest neighbors, it'll also include the diagonals and so on. Okay, so that's the delta vector. Okay, so then what I'm going to do is I'm going to take this formula and now I'm going to expand this. So I'm going to write this whole thing now as minus j a squared over 4, and then the sum over I, the sum over delta less than R, and then m of, let me write it like this in the continuum. So m of Ri plus delta minus m of Ri over a squared plus a term which is of order m squared, so I don't care about that. And then I can write this as minus j a squared over 4, sum over I, the sum over delta. And then I can write this thing inside by doing a Taylor expansion as delta dot grad m evaluated at Ri divided by a, and that whole thing squared plus order m squared. And then then I can replace the sum over I by an integral over space. So if I have a coordination number of the lattice little z, then I can write this as minus zj r squared over 4, and then integral d dr over a to the d, and then grad of m of r squared plus order of m squared. And so that means that I can write this then as minus some gamma grad m squared integral d dr. And then this gamma is then something like gamma is equal to the r squared times j times the coordination number over 4a to the d. I think all the factors are correct. So now what I've done is this form here for the free energy is exactly what we guessed when we construct things in the way that that we did phenomenologically. And let's see, there's another thing that's missing here. Oh, this should be, I think that this should be a plus sign because we've integrated by parts to go from here to here. Okay, so I think this ends up being a plus. Okay, so that's the so that's a sketch. It's not a full, detailed, rigorous proof. That's a sketch of how you can go from the microscopic Hamiltonian to derive this form of the coarse-grained free energy. So it just shows you the basic idea, but not it's not exactly rigorous. Andrew, question?
I don't exactly see how you went from one step to another where you have the gamma r plus delta extension.
I did a vector Taylor expansion.
So that's so how does the del
Delta dot grad n term come from doing the Taylor expansion. Okay, so try it after class, okay? Okay, so you know how to do a Taylor expansion if it's a scalar, or we're just doing it with it's a vector. Okay, so I don't want to be unhelpful, but I don't want to go through all the steps of that. Okay, I can discuss with you privately if you want afterwards. All right, now I want to go on to the next topic. Any questions about this? Any other questions about this before we go on?
So summation over I goes to the integral.
Yes.
And the summation over del goes to C.
Yes, that's correct. Thank you. Yeah. So let me just put that in just to make sure that nobody is confused about that. So this sum over I turned into this integral, just as we had before, and this z comes from this z comes from this summing over these deltas. That gives you that, which is why I introduced the coordination number up here. And then everything else is more or less self-explanatory, and this comes from just doing Taylor expansion and doing it to lowest order. All right, so now I want to move on to the next topic. So we're going to now talk about a renormalization group. So this is chapter 9 in my book, and we're going to approach this in a fairly phenomenological way. We're going to first start off by historical way. We're going to start off by motivating this in exactly the way that Leo Kadanoff did in a famous paper in 1966. And then once we've seen how that works, then we're going to improve it using the discovery that Ken Wilson made after 1971, after Kadanoff's paper, and improved his work. And I'll explain to you what it was that Kadanoff formulation couldn't do, and what was it that was improved in the final version of the normalization group. So our goal is a historical introduction. And the reason I'm doing it this way is because if you understand how you get the Kadanoff picture, then it's very easy to then, which is quite easy mathematically, it's then easy to extend that to the full renormalization group. So we're going to follow that. We're going to, the physics of this is going to be the diverging correlation length. We're going to explicitly focus on multiple levels of description. And this is the thing that Leo really did. Leo was the first person really to emphasize in this context how systems change depending on the scale at which you look at them. So that's the main ingredient that we're going to use here. And we're going to use the fact that, which we've already seen from mean field theory, that thermodynamic and correlation functions have singular behavior. So we know this already from mean field theory, and now we're going to exploit that. And so what is the goal of this calculation? We're not going to initially compute everything. So what we want to be able to show is, where do the singularities come from? Why are the critical exponents related to each other? And are different from mean field theory. We're not going to get a real answer to that until we do the real renormalization group. And then we're going to derive the phenomenon of data collapse, which we talked about a couple of lectures ago. And that was first discovered by Ben Widom and Leo Kadanoff. And they're not the only people who were involved in the development of renormalization group. There's others that I can mention, many others, including Jonah Lucinio, Palaszczynski, and Pokrovsky, and others too. There's a lot of history there. So this phenomenon of data collapse, which I showed you, is the thing that is going to be the crucial thing to explain. So this thing here is really what we're going to explain in detail. And the thing that we won't be able to do, at least for a while, for now, there's no recipe for calculating the value of critical exponents. And so all of this here is essentially what Kadanoff did, and then what Wilson added to this was how to calculate the critical exponents. And it wasn't just simply, well, here's a formula. There was a major insight into this, which is the phenomenon of scale interference, which I will talk about. And this is the thing that he understood and was able to explain how you really get everything. So let's talk about what we're going to be focusing on. So our focus in all of this is the singular part of the free energy density. So I want to make this very clear. because this is something that is, when people encounter phase transitions in the normalization group in non-condensed matter situations, they get very confused about this thing here. So let me tell you what I mean by this. So here is some data, and I'm just going to sketch some data. This might be, say, for the heat capacity of, let's say, a high temperature superconductor. And so the high temperature superconductor free energy heat capacity looks something like this. And then at TC, so let's say TC is here, what happens is you get this sort of little blip on top of it that looks like this. And if I were to expand this blip and zoom in on this blip, which is what we are essentially doing in this whole course, what that would look like is that's the thing that looks like this huge, power law divergence at TC. So that's the thing that we're interested in, but it's just a little blip on top of the actual heat capacity. So we care about the singular behavior. So this thing here is the singular behavior only. And this thing, this thing over here is our smooth background, which has no knowledge of the phase transition. And if you imagine that you're looking at a superconductor, well, in a superconductor, you have what contributes to heat capacity. You have phonons. Then you have the electronic degrees of freedom. When you go through this critical temperature, a very small fraction of the degrees of freedom are going singular and turning into the superconducting state. So the number of electrons that are contributing to the superconductivity is a vanishingly small number as I go towards TC. In fact, if I were to draw on this curve over here, if I were to draw on this, the order parameter, the magnetization, that would be 0 here. And then in this region, it's going up from 0 like that. Okay, so it's very, very small, vanishingly small as you go to TC. But its behavior near the origin, its behavior near here is singular. And that is the thing that gives you the singularity that you see in the heat capacity. So the order parameter, the magnetization, is vanishingly small as the temperature tends to TC from below. And so that means that it makes a very small contribution to the heat capacity. But because it has this non-analytic behavior, but its non-analytic behavior contributes 100% of the singular behavior. And that's why we're going to focus purely on the singular part of the free energy. So I'm going to call that singular part of the free energy. So Fs of T and H is what we're going to call. Let me write these as capitals for now. That is going to be the singular part of the free energy. And usually I'll write this as per spin, so I'll call it the free energy density or the free energy per spin. Okay, then I'm going to define H to be H over KBT, and I'm going to define little t to be T minus TC over TC. And so my free energy then becomes Fs of T and H, and we want to be able to compute what that is. Okay, so here's the basic idea. And it's really the thing that we've been talking about all along. We're going to coarse grain the system. So I have my physical system as looking something like this. So here is my box. We're thinking about a bunch of spins. So we might have some little blob over here where all the spins are pointing up. We might have another blob over here where all the spins are pointing up. And then the rest of the box, the spins are, all pointing down, something like that. So that would be our picture. And if I look at those blobs, the average dimensions of these blobs, they're typically of order the correlation length as a function of t. So that's going to be our characteristic size. So what we're going to say is we're going to look on scales which are much larger than the lattice scale A and much smaller than the correlation length t. And this L is an integer, at least for now. That groups spins into blocks of size L times A. So here's our microscopic lattice. Something like that. That's our microscopic lattice. And now what we're going to do is we are going to construct a block like that. So here's a block, an L by L block, and we're going to ask in that block, if all the spins are pointing up or mostly pointing up, then we can say that there's a variable in that block that has a spin value, and we're going to ask what is the effective behavior for those blocks. So what we're going to say is that in this block, in each block, compute the average spin value. And then the question we're going to ask is what is the thermodynamics of our blocks? So the basic trick is, in other words, we're going to replace all the spins in a block by a single representative spin. And that single representative spin is called a block spin. Okay, so that's the idea. So let's carry it out. So what we're going to do is we're going to say, well, how many blocks are there? So our answer is the following. I've got n original spins. I'm supposedly in d dimensions, although over here I've just drawn 2. So I'm in d dimensions. So how many blocks are there? I've got n original spins, and so therefore I've got n over L to the d block spins. So I'm going to label the blocks by capital I. Capital I is 1, 2, up to n L to the power minus d. The microscopic spins are Si, and I goes from 1 up to n. And how do I construct the block spin? Well, here's one way to do it. I'm going to define Si in the following way. I'm going to say, well, I'm going to take all the spins inside the block I. I'm going to add up their spin value, and then I'm going to divide by the net magnetization per spin of all the spins in the block times L to the D. Okay, so that's how I'm going to define this. And so this quantity over here, this is, if you like, the net magnetization per spin of a block of size L. So the way that we're doing it is going to guarantee eventually that SI behaves kind of like an Ising spin itself. So ML is going to be 1 over L to the D times the sum of the spins in the block, and then times the expectation value of SI. So that's what it means, and that's why we say it's the average magnetization. And so now what this means then is that SI is plus or minus 1, just in the same way that SI, our microscopic variables, can be plus or minus 1. So the way that we've constructed these blocks is that the block spins kind of behave approximately like the original spins. Okay, so then the question you would want to ask then is, well, what is the effective Hamiltonian that governs the block spins? Well, if we know that effective Hamiltonian, then that should allow us to compute the thermodynamics. So that's the question that we want to ask, and we aren't going to be able to answer it. We're going to answer it by making a strong assumption. So our answer is we don't know how to calculate it, but what we're going to do is we're going to make an assumption, which I'll call assumption number 1. Later we will learn how to calculate this, but you'll see why we're going to, for now, just make an assumption. So what we're going to assume is that at the microscopic level, we know that the Ising spins interact with their nearest neighbors. And so what we're going to assume then is that that means that the block spins also interact only with the nearest neighbor block spins. Later, we're going to actually calculate this explicitly and we're going to see whether it is right or whether it is wrong. But I'm just going to give you a comment just so that so I don't mislead you. So the comment I'm going to give you is that this is wrong. This assumption is wrong, but it doesn't matter. I'm not going to tell you now why it doesn't matter, but it's obvious why it is wrong. Let's explain why it is wrong. Let's suppose that my spins interacted in this way. Here's my lattice. Like that. And let's suppose that the spins interacted not with their nearest neighbor, but they only interacted with their next nearest neighbor. Okay, now that's not likely to be true. It can happen in some kind of disordered systems. So let's suppose it was that this spin interacted with this one, and then this one interacted with this one, and so on and so forth. Okay, so you only have next nearest neighbor interactions. So now let's suppose I make a block spin. And let's suppose it's, I don't know, 20 by 20. There's 20. So there's 20 by 20 block spin. Okay. Then you're basically going to see a big block spin. The spins interact with their next nearest neighbors, but you can hardly see those. It would be very weird if this block spin over here didn't interact with the one next to it, but only interacted with the one further away. So then you would have a weird picture, which would look like this. So there's my picture. You imagine I've got a block spin over here. Then I have its neighbor over here, and then its next nearest neighbor over here. And what we're saying is somehow these spins only interact with those and don't interact with the ones next to it. That would be completely weird. Okay, the next nearest neighbor interaction, the spins on the edge of that would be interacting with the block spin right next to it. So this is not physical. Okay, the spins on the edge of block 1, let's call this block 1. Let's call this one over here, which you can't see, block 2. And let's call this one over here block 3. So the spins in block 1, on the edge of block 1, will interact with spins in block 2. They won't just interact with the ones in block 3. So you can see that this is not correct. And we'll calculate that later. It doesn't matter. Okay, and that's the most amazing thing about this, that even though this assumption is wrong, it turns out not to matter. So that's assumption number 1. So why do we care about this assumption? Well, there's a consequence of that. Because we've just assumed what is the interaction between block spins. So now I can immediately then write down what is the Hamiltonian for the block spins. So the consequences then is that the block spin Hamiltonian in terms of the block spin variables, the capital S, capital I, in terms of those, will have the same form as the microscopic Hamiltonian. And so I can write it down. So I'm going to call it minus beta H L, and then I'm going to write it like this. And first of all, I'm going to multiply it by minus beta, just to stop having to write factors of KT and minus signs. The next thing is I call it this is a Hamiltonian. The L is the scale of the block spins, so that's what that means. And then what I've just told you is it's going to have the same functional form as the original Hamiltonian. So it's going to have a term that comes in here, like SI, Sj, and then there's going to be a term that comes in here, which will be the sum over I of Si. So it's going to have that form, the same form as the original Ising Hamiltonian, but there's going to be a coefficient in here, which is the external magnetic field, which will depend on the scale. And there's going to be a J over KT, which I'm going to write as K, capital K. That will depend on L. That will go in here. And so in this formula here, so KL is like J over KBT at the scale L. And then I can write down that my free energy, my thermodynamic free energy, is equal to over here, the trace over the microscopic spins of E to minus beta H. And then here in the middle, it's going to equal the trace over my block spins SI, E to the minus beta times the Hamiltonian at that scale L. Okay. Now then, so that's the first thing. Now we're going to do dimensional analysis. So the first thing about dimensional analysis is that the physical results of anything are independent of the units that you use. So as we already know, we can have a correlation length, which is the measured correlation length. It could be in meters, it could be in feet, it could be in parsecs, whatever you want. So that's the measured correlation length. At the microscopic scale, we might say, well, we should measure this in units of the lattice spacing A. So we'd say there's a number psi1 here, which is multiples of the lattice spacing A. So that would be one way that you could measure the correlation length. But you could also measure it in units of the block spin size. So I could also write it in terms of psi L times L A. So this now is in multiples of the block spin size, LA, like that. And so what that tells you then is that in those units, in the units of the block spin size, my psi L for that effective system is equal to the correlation length in units of the lattice spacing divided by L. So just by equating those two things together, that's what happens. Now, there's something now, a very important physical insight. What we know happens is that as we go towards TC, from above or below, the physical correlation length grows. Okay, the physical correlation length, say, is measured in the natural units of the problem, which are the lattice spacing. So you can see that psi L is less than psi 1 because L is a number that is greater than 1. And so what that means is that effectively the temperature of the block spins is further away from Tc than the temperature of the microscopic spins. By construction. And so what that means is that when we are coarse graining a system and replacing it by block spin variables rather than microscopic variables, what we've actually done by doing this transformation of the variables is we've actually moved to a different statistical mechanical system with a different temperature. So the temperature has been changed by this coarse graining. This is an example of what is called renormalization, namely that as we change the scale at which we look at the system, the parameters that come into the energy and therefore the temperature are changing. So the temperature, because of the correlation, because the correlation length is smaller, it must be further away from the critical temperature. And so that means that we have a new effective reduced temperature where TL is going to be greater than our microscopic little T1. Okay, so that's the first example of a renormalization effect. We call this a renormalization. And we will be defining renormalization precisely later. Then the second thing is there's another renormalization. The coupling to the external magnetic field also changes. Excuse me. Sorry, thank you. So let's see how. So what we're going to say is we're going to look at this term, which in the microscopic Hamiltonian is sum over ISI times our coupling to the external magnetic field. And if I now rewrite this in terms of the spin variables, the block spin variables, then this is going to look like H times ML bar times L to the D times the sum over the block spin variables SI. And so I can write this as H sub L sum over I SI. And now I've got an HL, an external magnetic field, that now is related to the original external magnetic field by this term here, which we have to be able to compute. So this is this term over here is the effective external field at scale L, and that's the thing that we've just calculated. So now we've got so in summary, so to summarize, we now have explicit formulae from our assumptions for the effective Hamiltonian at scale L. And the thing about this is, the thing that's really crucial is that HL has the same form as the microscopic Hamiltonian. I.e., so you could call it H1 if you wanted, right? So that means L is equal to 1. So that means that if I now take HL and compute the thermodynamics that will have the same form as the thermodynamics computed with a microscopic Hamiltonian. All I have to do is replace H goes to H sub L and T goes to T sub L. So let's go ahead and do that explicitly. So what that means is that if I compute for the number of spins in the system, the singular part of the free energy per spin as a function of T and little h, then that must equal the free energy for the block spin. So it's a singular free energy. It's going to depend on TL and HL because we're now on the block spins. And how many block spins are there? Well, there's N L to the minus D. And so then what we've learned from this is that Fs of T, L, and HL, this is for the block spins, is equal to L to the power D times Fs of T and H. This is for the microscopic spins. And the most important part about this equation is that this Fs and this Fs, those are the exact same mathematical function, whatever it is. They have to be the same mathematical function because we by assumptions, we forced the statistical mechanics of the block spins to have the same Hamiltonian as the statistical mechanics of the original spins. So therefore, when I compute the thermodynamics, I'm going to get the same functional form. It's just that the parameters are going to be different. So this is a functional equation. And we don't know what the function f is. Function fs has two arguments, let's call them x and y. We don't know that function, and we don't know the functions TL and HL. We know how they're defined, but we don't know what those functions are. Okay, so now the next step is assumption number 2. This was Kazanoff's assumption. He said, near the critical point, all the thermodynamics and the correlation lengths and things like this, everything is growing as a power law. So I'm going to assume, without justification, I'm going to assume that TL also behaves like a power law. So I'm going to say it's related to T, the reduced temperature, because it's the same functional, it's the same dimensional variable, whatever it is. And then it's going to depend on L, and we're going to say it depends on L to some exponent, which I'm going to call y sub t, where y sub t is greater than 0. And I'm going to assume that h sub L is equal to the original h times L to the exponent yh. And we're going to make this assumption. We assume this just because everything is going like a power law. And in fact, Kazanov was deliberately making this assumption, knowing that if he made this assumption, he would be able to get power law behavior. And now we'll see how to do that. So if we make this assumption, then the consequence is that our equation for the singular part of the free energy now has this form. It goes as L to the minus D, Fs of T, L to the power y sub T, H, L to the power y sub H. Has that functional form, and not any function will satisfy this equation. Only very specific functions. So what we're going to see then is that next time we will see what kind of functional forms obey this functional equation. And the most important thing about this, I want to stress, is that we didn't say what L is. So L is arbitrary. So it can vary to whatever you like. So there is a symmetry now in this equation, which is as I vary L, it has to conspire that as I vary L inside the function Fs, L appears inside the function here, it appears here, and it appears out here. It doesn't appear on the left-hand side. So L is arbitrary. So there must be a conspiracy that vary L somehow the right-hand side ends up being independent of L, even though L appears explicitly. Now, how do we know that it's independent? We know that it's independent because the left-hand side is independent of L. And this thing here, this conspiracy, as I called it, this is a fantastic symmetry that we've just created, the particular kind of symmetry. It's a scale, in this case, it's a scale invariant symmetry. It implies what is called a renormalization group equation, and only certain functional forms for Fs will obey this symmetry. And next time, we'll talk about how we solve this equation and what its implications are. Okay, so that's the end of today's lecture. So let me stop Zoom, at least stop the recording.